Buongiorno a tutti, io sono Silvia Todros del Dipartimento di Ingegneria Industriale e vi do il benvenuto a questa seconda giornata di conferenza. Inizio con un paio di comunicazioni. Gli atti della conferenza sono pubblicati sia sul sito della conferenza che sul sito del Gruppo Nazionale di Bioingegneria. Li trovate in due formati, un formato PDF che potete scaricare interamente e un formato navigabile, quindi con dei link che vi facilitano la navigazione dal menu. Vi ricordo anche che anche oggi dalla sessione orale potranno essere assegnati fino a 2 premi e la premiazione avverrà venerdì pomeriggio alle ore 16. Quindi invito tutti coloro che presenteranno ad essere presenti. Il premio è anche abbastanza interessante, diciamo che siamo arrivati intorno ai 1.000 euro a premio, quindi penso che valga la pena di essere presenti per ritirarlo personalmente. Vi presento ora i chair della sessione di oggi: Marta Parazzini del CNR, Mara Terzini del Politecnico di Torino, Luigi La Barbera del Politecnico di Milano e Emanuele Carniel dell'Università di Padova. Lascio ora la parola a loro e vi auguro buon lavoro.
Thank you, Silvia. Good morning, everybody. It's a pleasure for me to introduce this oral session number 2. And actually, within this session, we will have 3 presentations from track 3, Biomechanics and Prosthetics, 3 presentations from track 6, Neural Engineering and Micro and Nanotechnologies, and 2 presentations from track 8, Design and Validation of Biomedical Devices. If you have any questions, we will have time at the end of the 4th presentation and at the end of the last presentation. And so let's start with the presentation, and I ask to Luigi La Barbera to present his work entitled Assessment of a Parametric Thoracic Spine Model for the Generation of In Silico Cohorts. Okay, you have 10 minutes.
Thank you for your kind introduction. Good morning, everybody. I have the arch task to guide you through this first session, so I hope to be gentle enough. This presentation faces the topic regarding the assessment of a parametric thoracic spine model. For the generation of in silico cohorts. Okay. Typically, in the field of orthopedic and spine biomechanics, we are often using patient-specific spine models, which relies on a very detailed anatomy derived directly from clinical images and obtained through segmentation. The main limitation they have is that the mechanical properties are often derived from literature. The functional spinal units that are included in the model are limited, and it's difficult to generalize a patient-specific model to entire population, where maybe we need to test, compare a surgical technique or a treatment to better understand how an implant interacts with the biomechanics of the spine. In order to overcome this limitation, we could use parametric spine modeling, which offers 2 advantages. The first one is the time constraint, because we don't need to reconstruct clinical images, so we can quickly develop the spine models to support the clinical and surgical decision-making process. Then we can also use this parametric model to scale up and to obtain a very wide cohort of virtual patient that we can then use to build up finite element models with controlled features. The objective of this presentation are to develop a fully parametric thoracolumbar spine model implemented into a CAD model, SolidWorks, based on few independent parameters, and then to demonstrate the feasibility to translate this CAD model to finite element model, and then we will focus on a representative thoracic functional spinal unit, including 2 vertebrae, and the soft tissue in between, plus 1 rib, and we will calibrate the mechanical properties based on in vitro literature data. So for the first part of this this activity, we took inspiration from the anatomical measurement from Punjabi et al., published in the literature, and also from Kunkel, which are relating and measuring in a very accurate way the complex morphology of each vertebrae and disc. The workflow is based on a regression analysis where all the dependent parameters measured by Punjabi and Kunkel were linked directly through a best fitting with a third order polynomial function to one specific independent parameter, which was chosen as to be as the vertebral body posterior 8. Then we correlated the parameters for each vertebra, for each spinal level. We obtained an equation, which was then directly implemented into SolidWorks to build up a parametric CAD model. Here you see the interface where for each dependent parameter you have the calculated value, and you see that we have all the polynomial function which describe his function as a function of VBHP, which is the only independent parameters. Here you have a representation of how a lumbar and thoracic vertebra look like, accounting for generalized, simple enough geometry in order to take into account for the morphology of each vertebrae. When quantifying the prediction error obtained through regression analysis, we were quite happy because it was much lower than the measurement error by literature data, and also even in the worst case, which is this parameter where we have a root mean square error up to 30%, we can see that actually there is a good matching with the experiments. So we were at the end of the day quite happy. Then we introduced 3 additional parameters: thoracic kyphosis, lumbar lordosis, and the sacral slope, which are widely used in the clinical practice to describe how the spine is aligning on the sagittal plane. Here you see an average spine model, just to see that we are describing it in a good way. And here you see the range of values measured in vivo by 2 literature studies. And you see that the model, an average model, perfectly fits within this range. Then, if we are playing with the parameters, of course, we can achieve different kind of spinal alignment to fit whatever shape we would like to. Okay. Then we focused on the rib cage and the sternum, which for the moment were derived from the clinical measurement from literature. And then we introduced the rib cage, which is articulated with the vertebrae and the spinal processes. And here you see the entire assembled thoracolumbar spine with an anterior and a posterior view, with details of how each spinal unit is articulating with each other. To demonstrate that it's feasible to translate a nice parametric CAD model to a finite element model for structural finite element analysis in Abacus, we selected one spinal unit representing the thoracic spine, including 2 vertebrae, the soft tissue in between, and the ribs. At this stage, we decided to perform a calibration of the mechanical properties of each component of the functional spinal unit, simply comparing with the in vitro measurement from Wilke. And in particular, if Wilke was taking into account for a stepwise reduction protocol, where we start from left to right from a very complex intense spine, and then we subsequently remove step by step, for instance, the supraspinous ligament, the interspinous ligament, and so on, up to a simple model where we only have the 2 vertebrae and the annulus fibrosus, then we could take a backward stepwise calibration approach, where basically we started with a simple model, and then we calibrated the mechanical properties for each structure, matching the in vitro measurement in terms of range of motion, which describes how the functional spinal unit is moving. And then we were able to calibrate step by step all the mechanical properties of each tissue. Here you have an example. For instance, in the first step, we were assuming material properties from the literature for the cortical and trabecular bone and the end plates, which were cartilaginous. And for the annulus fibrosus, we took an anisotropic hyperelastic model. And it took 7 iterations to identify the right mechanical properties. And the results is here presented in terms of range of motion inflection, extension, lateral bending, and axial rotation. And you see that we have a good matching from between the finite element model that we just built and the in vitro experimental data. Of course, we continued with this process, iterating with the next step, which was nucleus pulposus and so on, and we were able to add all the soft tissues in between the two vertebrae, and this is how the results look like. So we see that a trend which is decreasing for each movement, and which is in well agreement with in vitro data. Here you have details about the mechanical properties also of the ligaments, which were described through linear spring, tension-only spring. In the next step, we also added the left rib. In this case, we were comparing with in vitro data by Lemos and colleagues. So here you see how the comparison with the in vitro data looks like. And again, you see that there is a stabilization, so a reduction in terms of range of motion as we add more structures. So for instance, the intercostal transverse ligament and the other vertebral ligaments. Here, more details about the mechanical properties. And then the last step was to add not only the left ribs, but also the right ribs plus the sternum. And here we compare with the data by Libsch. And again, we observed a very nice comparison with the in vitro data, which should support that at least we were able to not only describe nicely the geometry, the morphology of this functional spinal unit, but also to identify and calibrate the mechanical properties for each structure. So to conclude, we built up a simple parametric CAD model to describe spinal morphology and sagittal alignment. We only have 20 parameters, one vertebral height for each vertebra, so in total 17, plus 3 sagittal balance parameters, kyphosis, lordosis, and sacral slope, which makes this model rather simple to be used and simple to be implemented also by people who are not really friendly with CAD models and have a very limited understanding of the spinal morphology and anatomy. We also demonstrate that it's easily and prompt to translate the CAD model to a finite element model for biomechanical analysis. So the next step are to fully parameterize also the rib cage in also to build up that region and to calibrate and validate the whole thoracolumbar spine, so extending the validation also to the lowest lumbar segments. So with that, I would like to acknowledge all my co-authors and of course you for any question. Thank you.
Now we will have a presentation by Simone Ranaldi, which is entitled Synergy-Dependent Patterns of Reaction Forces in Sit-to-Stand Movements. Okay, you have 10 minutes.
Okay. Should I go?
Ah, sorry.
Okay. Thanks for the introduction. Today I will be presenting some results about an experiment on neuromechanical characterization in general of the sit-to-stand movement, and specifically why sit-to-stand. Sit-to-stand is a widely used clinical test as means for characterizing biomechanical performance in general in patients or healthy people. And typically this test relies on very short and comfortable protocols, such as 5 times sit-to-stand, so just rising 5 times, or 30 seconds sit-to-stand, so carry out the maximum number of movement during 30 seconds. And considering the fact that it's a very short protocol, this protocol is typically also carried out in an instrumented fashion in order to maximize the information about the control and the performance of this kind of biomechanical task. And as an addition to that, also some neuromechanical characterization can be made if some relevant data are recorded. And specifically in this case, we aim to insert muscle synergy analysis as a means of understanding how the different muscles coordinate to generate the movement during a very short task, and again, to maximize the kind of information that we record from that. The aim of this work has been twofold. One is to, in general, evaluate how different features coming from different analysis related to muscle synergies translate to different biomechanical patterns of reaction forces, external reaction forces. And on top of that, also to highlight the importance of having a set of objective and optimal tools for muscle synergy analysis, because as we will see, methods for extracting muscle synergies and muscle synergy related information vary across experiments, so that in the case of these short and compact experiments, we need optimal methods in order to extract the information. So in order to do so, we recorded data from 12 healthy subjects performing a basic 30-second sit-to-stand trial. We used an instrumented chair developed during the bench project, which is basically a chair that has been instrumented with two force platforms, one for the ground reaction force and one for the seat reaction force, let's say. And of course, together with that, we recorded the electromyographic signal from 8 muscles of the dominant leg in order to be able to extract the synergies regulating the movement during this task. The extraction of the muscle synergies has been made with standard procedures, so non-negative matrix factorization, aiming to factorize the activity of the 8 different muscles into those two matrices, W and H, which represent W, the relative weight of each muscle to each synergy, so the specific group of muscle that is activating together to generate movement, and H is the time activation coefficient of each of these motor modules, so that we have a compact description of which muscles are acting together and when they are acting. Of course, in order to do so, we need to fix the number of muscle synergies with which we want to describe the movement, and this is the point in which the literature is highly variable. So we developed an optimized criterion based on the Akaika information criterion in order to select the correct number of synergies. Those results there relate to different conditions in which we also optimized the length, the number of cycles that needed to be considered to extract synergies. After that, we fixed kind of a number of synergies related to 4, that's the maximum value that you see there, and when we extracted the profiles, we also carried out a clustering algorithm in order to extract the average profiles, let's say, so the common profiles among subjects. And we tried to relate these to the average force profiles of the different subjects. These curves here are related, as I said, to subject average, to average between subjects. When we go to the subject-specific information, that's something that we can do due to the optimal criterion, we see that the number of synergies that is actually able to describe the movement varies across subjects. And basically, all the subjects have at least 2 synergies, and some of them have 3 or 4. So that's why we determine with the clustering approach, which were the 4 profiles, the 4 activation profiles that we had in our population. And you see that basically 3 out of 4 profiles are composed of 2 activations, so one during the standing phase and one during the sitting phase, while one is kind of in the middle between the standing and sitting phase. So we used this information about the number of synergies in order to cluster the data coming from the force profiles. And we see that basically the subjects that were characterized by a higher number of synergies, so a higher complexity of the movement, so more modules that act to the movement, are also characterized by higher ground reaction forces. Okay? So the forces that are exchanged with the ground platform, not with the seated platform. And also, we have the same behavior in the anteroposterior component of the seat reaction forces. And we have also an interesting feature that's the three synergy conditions. So all the subjects that were characterized by three synergies have kind of less variability on the mediolateral component of the ground reaction force, the bottom right graph there, while the other two conditions are characterized by a more phasic activation that's in this specific condition out of phase between the two conditions. So we can kind of conclude this work by looking at the two different aims that I defined before. So first of all, we were able to highlight neuromechanical information about the movement during sit-to-stand due to the fact that we had the optimal criterion to determine the number of synergies, so that we were able to translate the information that were on an average across subject basis onto a subject-specific basis, so dividing the subjects into different number of synergies. And this allowed us to compare the results related to the neuro part, let's say, so the synergies and the number of composition of synergies, to the mechanical part, aiming to complete neuromechanical description of this kind of movement. And by doing so, we were able also to conclude something about the control of movement. So basically, it seems that the sit-to-stand movement is basically governed by the activation of two different motor modules, and that the presence of additional synergies is typically required when bigger reaction forces are involved, probably in order to manage equilibrium and stability during. But if we look at something related to the energy, some additional results that I drew here, actually the energies that expenditure, so the energy of the movement, is higher when we have a lower number of synergies. This might represent the fact that when having two modules, so a lesser number of modules, we have less feedback mechanisms involved, and the movement kind of represents something that is more feed-forward and just a ballistic movement of the subject launching itself in order to stand from the seat position and launching itself back to get seated again. And with this, I conclude, and I thank you for the attention.
Okay. I would like to invite to the floor Anna Ramella from Politecnico di Milano, who will talk about a numerical finite element methodology of the EVAR procedure. Please, Anna.
Thank you for the introduction, and good morning, everybody. With my presentation, I'll show you a methodology to model the TEVAR and EVAR procedures. EVAR and TEVAR are two minimally endovascular techniques that are used to treat aortic pathologies. The difference between the two is that the TEVAR involves the treatment of the aortic arch and the thoracic aorta, while the EVAR the abdominal aorta. The procedures consist of implanting a self-expandable stent graft into the pathological region to recreate like a more physiological condition. And stent grafts are composed of a nitinol stent sutured to a polymeric graft. For TEVAR, stents are composed of a single main body, while for EVAR, stents are quite more complex because they involve the main body with the bifurcations and one or more limb extensions that will be implanted as well. Those procedures have a high short-term success, but some complications arise in the long term because of the presence of the device. And in this field, the numerical analysis can help. In particular, the finite element analysis is largely adopted to replicate the procedures themselves and to study the biomechanical interactions between the device and the vessel. And for example, in the deployment simulation approach, many approaches are present in the literature, but I will focus on the tracking method, which is the one that we developed specifically for the TEVAR case, but in this presentation I'll show you how this methodology is applied to model the EVAR procedures involving a commercial stent graft.
This is the outline of the presentation, and I'll start with showing you how we develop and validate the methodology for the TVAR case, and then I move to the EVAR. So we have a commercial stent graft model that we discretize with beam elements for the stent and membrane elements for the graft. We include the stent pre-stress features because we see that when we remove the sutures between the stent and the graft, we found out that the stent diameter was larger with respect to the sutured one. So we include these features that we call stent pre-stress into the model. And regards the mechanical properties, but for the graft and the stent, we calibrate the material parameters of the simulations by using experimental tests. So the graft was modeled with a fabric material and the stent with a nitinol shape memory alloy material formulation. Given the old stent graft model, then we validate the device model by comparing our simulation with the experimental data. In particular, we perform crimping tests on real devices, and we compare the results with the simulation ones, obtaining a good agreement, thus validating the device model itself. Then we move to the simulation of the implantation. And again, we combine experimental with numerical approaches. For the experimental, we 3D printed a rigid patient-specific model, and under CT, a surgeon implanted the stent graft, and we performed different CT acquisition and different instants during the deployment, and we managed then the CT with VMTK. And then we move to the numerical side, and we develop a finite element explicit simulation, which consists of those 3 steps, which are an initial crimping of the device, a tracking of the device into the vessel to reach the correct landing zone, and a deployment of the device from a proximal to a distal region. So we compare our experimental results with the simulation ones, both qualitative by performing an overlapping between the 2 results, and also quantitative by calculating for each stent strut the opening area error, which is the opening area of each stent strut between the simulation and segmentation. And we obtain errors below 5%, which are much lower with other literature data. So this is about the TVAR procedure that was validated. So we decided to try and apply it to the EVAR case. So we start with those 2 stent graft models, which are quite different because the second one has 2 iliac extensions, and we recreate the numerical models first of the stent struts, which have different shape along the length of the device, and then we combine them into the complete stent graft model. The material parameters and the mesh are the same of the one that I showed you before, because those devices were produced by the same company of the device that we studied for the TVAR case, so same material properties. And the aortic model, we segmented it from with VMTK and from preparative CT images, and then we modeled it as a rigid body. So we apply the methodology to the EVAR case. These are the components of the simulations, and again, we perform explicit finite element simulations. First, we implant the stent graft main body, and then the iliac extensions. As before, we have an initial crimping phase of the device to reach the correct diameter. Then the device is displaced inside the catheter until the proximal landing zone is reached. And then the device is gradually released into the vessel. These same steps were also applied to implant the limb extensions that you see at the bottom of this slide. And then we move to analyze some results which can be interpreted as some indicators of some clinical indicators. For example, here I plotted the distances between the stent graft and the aorta, where you see that distances are low in the proximal neck length. In the proximal neck, meaning that the graft is, and the stent is well opposed to the aortic wall. And also, of course, in the femoral artery, because the diameter is very lower with respect to the device. We analyze also the strain on the graft, which are higher where the graft presents some foldings, and also the stress distribution both in the main body and in the limbs, but also in the main body after the limb insertion. And you see that after limb insertion, the stress reaches higher values. And then we look at the von Mises stress on the stent, and we see that the von Mises stress are higher at the proximal neck, where the stent was not fully expanded and didn't recover the initial diameter. So to conclude, starting from a methodology that was specifically developed for the TVAR case, we apply it to replicate the EVAR case. So we reproduce the stent graft model, and we implant the stent graft main body and limb extension. However, these models still need to be validated, as we did for the TVAR case. So this is like a proof of concept study. But with those studies, we were able to analyze some parameters like distances or stress strain distribution on the device, which can be indicators of the outcome of the procedures. And in the future, more patient-specific anatomies can be involved, more models of stent grafts can be studied to make this model used by clinicians in the procedural planning phase. So I would like to thank my research team and you all for the attention.
Then the next speaker is Felicia Roffo from Università di Napoli Federico II, which will tell us about coupled hydrodynamic flow, focusing to design lipid polymer NPS lipons for theranostics. Please.
Good morning. Thank you for the presentation. Nanomedicine has changed the way nanomaterial interact with the living organs due to unique property respect to bulk materials. However, up to now, only the 0.7% of the injected nanoparticle actually reach the target size. And this is due to this imbalance, is due to the filtration, sequestration exerted by biological barrier on nanomaterial. Actually, the design paradigm is based on physical perspective rather than biological perspective. When we talk about physical perspective, we are thinking about the materials and the physiochemical characteristics of the nanoparticle, but not the insertion within a biological environment. In this sense, for an optimal design, we need to start from the analysis of the biology of the target disease. Then we have to identify which are the biological identity that must be acquired by the nanoparticles, and then define manufacturing procedure in order to obtain physiochemical property that guarantee that biological identity. Therefore, it is necessary to have an approach that is quality-oriented. We can say quality by design manufacturing. Indeed, for a personalized and precision medicine, we need to have an easy and translational clinical approach with a ready-to-use nanoparticle, even clinics. In this sense, if all of these steps are working efficiently and we know the dose and the potency of the drug, we will think about reducing the dose of nanoparticles to deliver it at the target site. What we know now is a lot about biological barriers spanning from blood circulation to the cells and the somal escape, but the rate-limiting step now is the tumor tissue that is represented by the extracellular matrix that is made of hundreds of molecules that are bounded and assembled that make a three-dimensional network that hinders the penetration of nanoparticle to target site. And in this sense, a lot has been done in order to characterize the nanoparticle size, shape, and charge, and recently new evidence is reported that indeed the elasticity is a new parameter that can help to improve the nanointeraction of the nanoparticle before reaching the cells. Indeed, we saw that there are evidence that there is a high blood circulation time of soft nanoparticle than stiffer one, because they are less sequestered by the macrophagy, but also they are less removable by the filtration system for their deformability. Indeed, up to now, the most commercially available nanoparticle in nanomedicine are soft one. Let's think about lipid-based carrier. So this elasticity can be also declined as fluidity for lipid-based material. And we talk about fluidity when we can mix and add new components like cholesterol to the lipid mixture in order to provide them new elasticity or fluidity. In this sense, there are evidence that there is an increasing of the tumor penetration for these tunable fluidity and elastic particles. But what is most interesting is that by changing the elasticity of the nanoparticle, we can switch and shift from among cell internalization pathway. Gu et al. Reported by changing the elasticity of nanoparticle from pure liposome to a complex hybrid structure, we can shift from a competition between fusion and endocytosis to a pure endocytosis process. And starting from this consideration in mind, we would like to explore this elasticity with an hybrid vector that gives us more structural support, so in polymer core covered by lipid bilayer, and also the lipid bilayer can provide to the tool this fluidity and cell mimic behavior that help us at nanobia interaction before reaching even the cells. And we design a microfluidic platform in order to complexate this material. In these are sophisticated nanoparticles that require an high control on the process condition. Indeed, generally, the hydrodynamic flow focusing that is implemented in the literature is performed by injecting the middle phase here a lipid and polymer component that is squeezed by two side buffer streams that reduce the solvent concentration and therefore trigger precipitation. Differently, in our process, we decide to inject in the central channel a ketosane solution and the side channel a lipid dissolved in ethanol water streams. In this sense, all our inlets are the main players in the thermodynamics. Indeed, each of the channels is involved in own thermodynamic process, but also influence each other. Therefore, we are coupling both thermodynamics in one step process. Of course, here is important the component confinement, but also the mutual interdiffusion of each solvents in the other phase. Therefore, we compute a COMSOL simulation in order to understand how the solvent interdiffusion happens along the channel width by spanning all the channel device, and we make an insight on the fluid interfaces. Starting from this study, we then make an experimental campaign in order to understand and visualize which was the window in which this coupling was maintained. So starting from this platform that was an hybrid platform, we applied these nanotools to a case study. Indeed, we want also to improve the delivery of microRNA and therefore improving its delivery at nano-bio interaction with this hybrid tool. Indeed, there are a lot of challenges in systemic delivery of microRNA about stability. So before injecting in the device our microRNA, we made a preliminary study about the stability of microRNA in endogenous condition when we check their stability. What we made, we checked the stability of microRNA at different temperature, at different pH, and also for component addition. Then we injected the antisense oligonucleotide in the central channels, and we had also a contrast agent component that was the gadolinium DTPA. So we provide to the tool a theranostic property. Indeed, we checked that nanoparticles, we checked the nanoparticle size, charge, concentration, thanks to the nanosite instrument, and also we checked for morphology of nanoparticle. Moreover, we saw that effectively there is the loading of the contrast agent within the nanoparticle by computing the longitudinal station time distribution of the nanoparticles. Then we effectively checked the functional activity activity of this antisensory nucleotide through the targeting of their two gene PDCD4 and P10, and also by checking the migration ability of the cells. What we see that effectively there is a regulation of the microRNA 21 and upregulation of the relative to target genes. This study was made in comparison with the common transfectant agents. We checked also the biological effect of the nanoparticle on the migration ability of the cells. So with in mind the consideration that we made about this hybrid tool in the nanobio interaction, we made an insight and study on the interaction of nanoparticles with the cell for 48 hours every 80 minutes with an high content live imaging technique that provide us information about the cell motility, proliferation and morphology. Indeed, we computed, as is possible to see, which we saw that nanoparticles change the cell shape in the first for 6 hours of acquisition. Indeed, on the x-axis is reported the time, and on the y1 the parameter of interest. And what we saw that for the first 6 hours there is a change in the morphology of the cells that end with the recovery after these 6 hours. But what is interesting that after 18 hours of the interaction there is an increasing of the median length with duration of the cells. Therefore, we checked this data with the data about the cell motility and proliferation. What we saw that in the same framework of interest, we saw that there is an increasing of the instantaneous cell velocity that was computed as the cell velocity of the cell in each transition of the framework of acquisition. Then we checked for the cell proliferation, and we saw that effectively the lipid polymer nanoparticle reduced the cell proliferation of the cells. However, by checking to the mitotic index that give us the number of cells undergoing a mitosis over the total number of the cells, we didn't see a big difference between the cells treated with the lipid polymer nanoparticles and the control cells. So we thought that it's true that the lipid polymer nanoparticle, let's say, is slowing down the cell machinery of the cells, but the cells are not losing the capability of undergoing a mitotic event. So to understand if this effect was of the materials or the nanoparticle, we made a comparative study with the polystyrene nanoparticle that are commercially available nanoparticles, and we didn't report any difference of the cell morphology upon the interaction with the polystyrene nanoparticles. However, we cannot make any statement about the median cell velocity of the cells because the time of acquisition which we made the experiment was not enough to see any effect of lipid polymer nanoparticle that happened after 18 hours. So what we saw that effectively lipid polymer nanoparticles, so hybrid system, can use as a platform for targeted delivery. Indeed, we reported also an innovative approach for that is a microfluidic approach to couple thermodynamics in order to have a quality by design approach for translational medicine. Moreover, we validate the ability of this hybrid system to be stable themselves, but also to deliver a stable compound. And finally, we made the preliminary study about the interaction of this tool with the cells. Therefore, the optimal design is very complex problem that requires the understanding of a lot of parameters that interesting the bioengineering, starting from the analysis of the clinical data to define which are the biological identities and synthetic identities that must be coupled in order to reach the target site. And finally, we presented the idea that before thinking about delivery nanoparticle to the cells, we have to target first other biological barrier where one of the main players is the extracellular matrix. Therefore, an elastic tool or fluid tool can be used to target the biological barrier that up to now are not reached properly. So thank you so much.
So we invite the first four speakers on the floor to start for Q&A. Okay. Any question from the audience? I will break the ice, I think. I have a question for Luigi. Actually, two. You use actually primitives geometries to recreate the complex geometry of the spine. And I was wondering if a statistical approach could be used starting from patients' data to recreate the entire anatomic geometry starting from, for example, principal component analysis or partial least square regression to obtain a more anatomic, let's say, geometry. And the second curiosity is if the meshing procedure is quite automatic or it's repeated at any new geometry, and if any mesh morphing technique could be used just to automate also this step.
Okay, thank you very much. So regarding the first question, of course there are in the literature very different approaches. Maybe there are approaches based on clinical data, on huge databases where you can definitely study statistically how the shape of the spine is changing, for instance using principal component analysis. This is an approach that has been already established in the literature by other groups. We didn't have any huge database good enough and complete enough to take that pathway. That's why we decided to go through the literature to see, to have a more, let's say, maybe less precise but more simple representation of the spine, which was good enough not really to follow, for instance, the geometry of the spinal process, the facet joint, but to have a generalized, let's say, description. Then regarding the second question, of course, you could use, and this is the plan actually, to use a morphing technique in order to mesh any CAD geometry that you could imagine, simply recalling one simple mesh that has already been established on the entire average thoracolumbar spine. And in this case, you just need to identify some specific meshes, some specific landmarks to change the shape of your mesh, and then to morph it to a new mesh, to a new CAD design.
Thank you. Other questions?
I have a question for Anna Ramella. Within your model, you assumed rigid body behavior for the aorta. What do you think it would happen if you assume deformable behavior, and what do you think about performing FSI simulation of the system?
Yes, thank you for the question. So for now, for the EVAR case, we are using a rigid model because we are still let's say, modeling the device. We are focusing on the device, so we exclude any uncertainties related to the deformability of the vessel wall. For the TIVAR case, we have performed simulation with deformable vessels. We include a deep stress on the vessel wall, so we are, the project is more, yeah. Instead, for the EVAR, is just a preliminary study. We wanted to try to apply that methodology that was already validated for the TIVAR to the EVAR case. And regarding the FSI simulation, yes, for the TIVAR case, again, we are doing FSI simulations of the vessel with the stent graft implanted. We still have to validate them, but we are working on that. Instead, for the EVAR case, again, we just performed those preliminary simulations, so it's still an ongoing project.
Okay.
Thank you.
I have a question for, I think, one last question for Simone. You described the AC Akaiki methodology to select for the optimal model, selecting between two or more synergies. And if I well remember, AEC select models based on the minimum numbers of parameters and the best, let's say, goodness of the fitting, but it does not wonder for cross-correlation between the selected parameters, and I think that synergies are quite cross-correlated. So how do you manage this?
Yeah, the thing is that, of course, the performance parameter is how well it reconstructs the muscle activity. The number of parameters comes from the number of numbers that are actually in the W and H matrices. And the thing is that the higher the number of synergies that you extract, the bigger those matrices, because they have to describe the matrices. The problem, the issue with the typically applied AC criterion is that EMG envelopes are typically oversampled, and the sampling frequency is higher than it should be for the sampling theorem. So we needed to find a way to calculate how many of those samples, of those time samples, actually were meaningful for the reconstruction. So that's why we modified the criterion in order to have an estimation of how many of the numbers that are actually in the W and H matrices are meaningful for the reconstruction. And then, of course, the performance parameter is the same. Okay. Thanks.
Thank you.
I have a question for Dr. Roffo. If there are other questions from the audience, please raise your hand. So you have described a very nice new technology to build this kind of nanoparticles. I was wondering if you have an idea of what could be the improvement in reaching the target by this methodology.
Okay. Also, we are still studying because, you know, with this kind of particle is based on the idea that tuning the elasticity and preserving the structural advantage, we can overcoming all the problems that are linked to lipid-based carriers and overcoming also the problem of polymer 1. We are now studying if the addition of peptide on the nanoparticle can improve the targeted delivery of nanoparticles. But this is not an easy point because the nanoparticles themselves, without the peptide, using the fluidity, can improve the targeting of the extracellular matrix. Indeed, the topic is this. We have to start thinking again about nanoparticle as a tool to target the ACM or maybe to avoid blood circulation rather than improving the cellular delivery of the carrier, because the cellular are the last step and we have a lot of barrier before. Therefore, one strategy could be the addition of a peptide on the surface of nanoparticles. The pegylation can be used, but on the other case, we can lose a little bit about the fluidity of the lipid matrix themselves. So it's not an easy question. We have a platform, we have a microfluidic platform that can give us the possibility of tuning material complexation. And this is the point, that we can change material, we can try other material, and how this material can provide new features and to triggering and to acquire optimal design nanoparticles.
Okay, thank you.
Thank you.
If there are no other questions from the audience, we thank all the speakers of this first part of the session. Thank you again.